Hello, in this video I'm going to talk about electron microscopes, and I'm going to go through two different types of electron microscopes, starting with the transmission electron microscope. So these are similar in a lot of ways to the optical microscopes that we use in the lab. You quite often use them in biology lessons at school, and there's a lot of similarities here in that we're going to have a backlit sample. This is what we have in optical microscopes, isn't it? You've got a light box at the bottom, you've got a thin slice of the sample, the light goes through the sample, gets connected by some lenses, and then we look at it at the top. You've got various structures of how we can have all the lenses, but essentially this is what's happening. We've got light, we've got sample, we've got lenses, and then we look at it. Now these transmission electron microscopes are pretty similar, but of course we're using the wave nature of electrons rather than using optical light, but we're going to see a lot of similarities. So our equivalent to the light box then is going to be an electron gun. So we have our electron gun down the bottom here. I'm going to draw this left to right, and we've got electrons coming out of this as a beam. So that's our electron gun. We want to focus this into a parallel beam. And in these electron microscopes, well, we don't have lenses like we do in the optical microscope. We have electromagnets which act as lenses. So we can set up an electromagnet here. So imagine this is a ring. I'm just cutting through the ring. So we're seeing top and bottom of the ring here. The electrons come out of the electron gun, and this first, what's called the condenser lens, will then focus these electrons into a beam. And I'm massively exaggerating this in the up-down direction here. The electrons aren't going over such wide angles, but if I don't draw them over wide angles, we won't be able to see what's going on. But still, we've got our electron gun, we've got our condenser lens, we've now got a parallel beam of electrons. This is where we then put our thin slice of sample, and the electrons then pass through the sample, hence transmission. They're going through the sample and we get diffraction. This is the wave nature of the electrons. So the beam spreads out. Now we get another couple of lenses. So again, slicing through the circular electromagnets. We've got the objective lens. So this will then focus the beams in a bit. So that will go something like that, and then we can have another lens. This can be the projector lens that will then create an image on a screen over here, whatever detector we're actually using to turn this into an image. So this is the projector lens. So we've got, in this particular setup, I've got 3 electromagnets here, and we're just manipulating the path of these electrons, having gone from the electron gun to the sample and then to the detector to create an image. So you can see it's got the same characteristics as the optical microscope. Here we've got light box, lenses, eye. Here we've got electron gun, lenses, and then detector. Now we need this inside an evacuated chamber because we don't want the electrons colliding with molecules in the air. That's just going to create blurring. As I say, we haven't got anywhere near the angles here. All the electrons are traveling within less than 1 degree from the central axis. So I've massively blown up the angles to make the path more visible. With the resolution of this, now the sort of resolution that you get in a sample depends upon the wavelength of the wave which is being passed through it. Now with optical light, we're getting 4 to 7 times 10 to the minus 7 meters. That is our wavelength for optical light. Here for these electrons, we could be getting 10 to the minus 10, we could be getting 10 to the minus 12 meters. So we're getting much greater resolving power because we've got a much shorter wavelength. Now there are issues, just as in the optical microscope, the quality of our lenses is going to also determine the quality of our images. We got the same thing here. The precision of the electromagnets will also determine the quality of the image. So it's not just down to the wavelength of the wave that's being passed through the sample. But even then, even with the difficulties in manipulating accurately these electrons, because the electrons have got a range of speeds. Yeah, even if they're coming out of an electron gun where we're trying to do a velocity selector on these electron guns, you're still going to get a little bit of a range of speeds. You're going to get a bit of blurring, because if you've got a range of speeds on these electrons, then the electromagnets, I mean, these are optimized for a particular speed. So you're going to get a little bit of blur in there. But yeah, the quality of your electron gun, the quality of your electromagnets will all add to the precision of your, the resolution that you're going to get out of your electron microscope. But even then, we're still getting maybe 1,000 times the resolution compared to an optical microscope. So that's the transmission microscope. The other one that I'm going to look at, I'll swap over to blue, are tunneling microscopes. So with these ones, we use the idea of quantum mechanical tunneling. So this is something which comes up in quantum physics and can get utilized in these microscopes. So let's think of, say we've got some graph here where on the x-axis we've got a position coordinate. So say we're taking a slice, one dimension in space, and on the y-axis we've got potential energy. Say we've got a potential energy barrier, so some barrier here which is stopping objects from moving from one part of our x coordinate to another part, another range of our x coordinate. So say this was a slice through a room. You might, if we're talking in classical mechanics, you might have a ball bouncing around in one part of a room. So it's bouncing around here on the left, and you've got a wall in the middle of the room. If the ball wants to bounce over the wall, as in over a potential energy barrier, it needs to have a certain amount of energy to be able to bounce over the top and get to the right-hand side. You might think of it in terms of our electromagnetism. So say you had two metal spheres, and if there's going to be a spark, an electron going from one sphere to the other sphere, well, there's a potential energy barrier between the spheres because you've got air between the spheres, which is acting as an insulator, and the electron will need a certain amount of energy to get from one sphere to the other. Now, all of this is how we've been thinking of it in classical physics. Now, if we're in quantum physics, you get this effect called tunneling. So let's draw this out again. So this is our potential energy barrier that we've got. So say we add an electron. We are dealing with electron microscopes. So let's think of an electron which is on the left-hand side of this potential energy barrier. So we've got a wave function for the electron. And, okay, a little bit wonky, but still we've got a wave function. And remember from the previous video, we were saying that the probability of the electron being in a particular space and time depends upon the square of the amplitude of this wave function. Now, when the wave function meets the potential energy barrier, it will decay exponentially. It doesn't just come to a stop and just end where the barrier is. It decays exponentially. And then when we get to the other side of the barrier, we've still got a little bit of the wave function. It's just got a smaller amplitude. So it's a lower probability that the electron will be on the right-hand side, but it's still a non-zero probability. You know, it's much more likely to be over here on the left because we've got a higher amplitude. So you square the amplitude, and that's telling us about the probability. Smaller amplitude on the right, but there's still a chance that the electron, even though it didn't have enough energy to go over the barrier, might have tunneled through it, and it might be on the other side. And this is the effect that we're using in these tunneling, or more fully, the scanning tunneling electron microscopes. So what these microscopes are doing is they are scanning a surface. So say we've got some two-dimensional surface, some surface which has got, we want to know what ripples are on the surface. It might look pretty flat, but we can get some great resolution here by using our scanning and tunneling electron microscope. So we've got this surface, and we're going to scan all over this surface. We're going to go through both dimensions of the surface, and we want to get how it's undulating. How rough is the surface? Let's look in detail at the undulations on the surface. So if I cut through here, so we've got something which is undulating around, if you get it at really high resolution. We're then going to have a probe. So you have a really sharp pointed probe which comes down. So the tip of this probe is 1 atom across. It's really sharp tipped. And we hold this probe. So this gap here between the tip of the probe and the surface is about 1 nanometer. We've got a 10 to the minus 9 meter gap between the tip of the probe and the surface. Now that gap is a potential energy barrier. We've got electrons sitting here at the tip of the probe, and we'll set up a small potential difference, say a 1 volt potential difference between the tip of the probe and the surface. So we want both of these things to be conductors. So the probe is a conductor, the surface is a conductor. And if we want to scan a surface that isn't a conductor, we can put a really thin coating, conducting coating on that surface. So we've got 2 conductors. We've got a 1 volt potential difference between them. We've got a potential energy barrier, and we've got an electron, well, we've got a load of electrons sitting here being fed down to the tip of this probe. Now, these electrons, some of them, will tunnel across the gap. They'll tunnel from the tip of the probe down to the surface. That will then cause a current to flow. We'll be able to measure a current in an ammeter coming off of this surface. If we can keep the current constant, then that means we're keeping the gap between the tip of the probe and the surface constant, because it's the width of this gap is determining the potential energy barrier, the size of the barrier, and the size of the barrier determines the current. So if we've kept the current constant, we've kept the gap constant. So by scanning across this surface, if we keep a constant current, the tip of the probe will be moving up and down exactly parallel, mimicking the structure, the structure of the surface, the different undulations on the surface. That probe will be moving up and down exactly in synchronicity with the contours of the surface that we're scanning. So we have to hook this up to various other things. We have these piezoelectric crystals. We came across these in our electromagnetism videos. So these are crystals which change size when a potential difference is applied to them. So we'll have 3 of those crystals which are attached to this probe. So 1 for the X direction, 1 for the Y direction, 1 for Z direction. We can then, if they're all perpendicular to each other, we can cause these crystals to contract and expand in a sort of feedback circuit to keep this current constant. And if the current is kept constant, we can scan all the way across the surface, record how the tip of the probe is moving, and that gives us the contours of the surface. So yeah, really high resolution electron microscope just for scanning surfaces. And it all depends upon quantum physics, because if we didn't know about quantum tunneling, then we wouldn't be able to build one of these electron microscopes and get them to work for getting high resolution scans of surfaces. So there you go. That's 2 different electron microscopes. We've got the transmission one, which is similar to a conventional optical microscope, but with higher resolution. And then we've got this scanning one for scanning surfaces using quantum tunneling. So there you go. At least that gives you a bit of an intro on how electron microscopes work.